Our next lecture is on radioactive decay. So you might remember from your grade 9 or 10 science course, a chemical reaction is the interaction of substances to form new substances. In a chemical reaction, the elements do not change. All of the elements that were present in the reactants are present in the products. However, with nuclear reactions, they involve changes in the nuclei of atoms, and they sometimes result in completely new elements. When this happens, the nuclear reaction is said to be a transmutation. So we will use a capital X as our parent atom and capital Y as our daughter atom. So X is the reactant, Y is the product. Note that they are not referring to any elements, X or Y. We're just using them as general elements, and you'll see what I mean when we write down some of these potential nuclear reactions. The identity of the element is determined by examining the number of protons in its nucleus. If the number of proton changes, one or more new elements result. So basically the element's identity is in the number of protons in its nucleus. So nuclear reactions involve changes in the nuclei of atoms. They sometimes result in new elements. That's known as a transmutation. The reactant is the parent atom, and we give it the symbol X. The product is the daughter atom. We give it the symbol Y. So a fascinating area of scientific inquiry around the turn of the 20th century was the splitting of the atom. And in 1896, Henri Becquerel observed this as a naturally occurring event when he found that a sample of uranium left an image when it was accidentally placed on photographic film. This eventually led to the discovery of radioactivity, the spontaneous emission of radiation. The process by which a radioactive atom spontaneously breaks apart to form smaller atoms is called radioactive decay. Radioactive decay is always accompanied by the emission of particles or electromagnetic radiations. It was the emission of the radiations that caused the film traces. So radioactivity is the spontaneous emission of radiation. Radioactive decay is the process by which the nucleus of an atom spontaneously changes. And when we have this decay, we have radiation. Becquerel's accidental discovery of radioactivity encouraged scientists to seek ways to induce similar reactions using various materials. These efforts helped other scientists like Ernest Rutherford and James Chadwick develop a better understanding of atomic structure at the nuclear level and form the basis for the broad range of nuclear scientific work that followed. In 1899, it was found that the particles from one form of radioactivity would pass through only a thin sheet of aluminum, while another would penetrate much thicker sheets. It was also discovered that these particles could be deflected by a magnetic field, and thus carried an electric charge. So these two kinds of radiation were called alpha and beta. So alpha radiation tends to be stopped by things that like a thin sheet of paper. Beta radiation can pass through that, but it won't go through something a bit thicker. And also beta radiation is electrically charged, as is alpha radiation as well, but we'll get into that shortly. In 1900, a third kind of radiation was discovered. This was a type of radiation that was very penetrating. We call this gamma radiation. It was uncharged, so it could pass through a magnetic field without any sort of deflection. One of the most common forms of radioactive decay is alpha decay. So we'll talk about the first one. That symbol you see is the Greek letter alpha. And alpha decay is when we have a helium nucleus consisting of 2 protons and 2 neutrons spontaneously being emitted from the nucleus of a radioisotope. So we start with our parent atom being an X with a atomic mass of A and a number of protons of Z. It then loses an alpha particle, which is a regular helium isotope, a 4-2 helium isotope. That means that the transmutation that occurs is our product particle Y, which has 4 less for its atomic mass and 2 less protons. Beta decay. If we look at beta decay, well, what we would do here is we would see that beta decay actually has a number of different forms, one of which involves the emission of an electron. So our A Z for our X there, it's A being its mass and the Z being the number of protons it has. It loses an electron, so its Z, its charge there increases, meaning that we have an additional proton, and it gives off this electron as a beta particle. And then we have, so that's referred to as beta negative decay. Then we have beta positive decay. This is when we have the opposite of an electron, something called a positron, which is the same mass of an electron but has an opposite charge. In this case, our proton count decreases, so our mass stays the same, but we have a drop in the Z, which is the number of protons. And the last type we have is actually called electron capture. So this is where the electron gets captured on the parent side of the equation. So it's X plus the electron, and it's equivalent to dropping a proton in terms of our Y value. And we'll look at sample questions that help explain these a bit better as well. Lastly, with gamma decay, this one's a bit different because the only thing that we're giving off is a photon, and the symbol for a photon is the Greek symbol gamma. It has a mass of 0. It has a charge of 0, so it is 0, 0 gamma, as you can see here. That is a gamma particle. There is no transmutation that happens in this case. So if we have helium giving off gamma decay, it would still remain helium. We just have the energy, the plus a photon, as our energy on the other side. So this is an important slide to copy down. The examples of alpha decay, beta decay, and gamma decay. Notice that there's 3 different types of beta decay, so there's 5 to know altogether. You may want to write this down and keep it with you when you write your assessments. Now, what do we mean when we have this X and we have these Z minus 2s and Z plus 1s? We'll look at a sample problem here. And you'll want to have a periodic table with you as you kind of refer to this. Here we have americium 254, and we're asked to draw americium 254 undergoing alpha decay. Well, the Z and the A for this would be 254 is our A, and our Z would be 95. The helium atom, the alpha particle that we lose, is a 4-2, so we have to drop our mass by 4, and we have to drop our protons by 2. And if you look at americium on the periodic table, and you move 2 to the left, you have neptunium. So americium transmutes into neptunium, and we have the alpha particle, helium, being given off as well. Next, we're asked to take selenium-81 and undergo beta decay. So to write down selenium-81, we would write down Se. The 81 is given to us as our mass. You would look at your periodic table to find out what is the atomic number of selenium, and it's 34. For beta negative decay, we are giving off an electron. That's our beta particle. And the proton count, or the atomic number, is increasing by 1. So we have, if we look at selenium, if we go 1 to the right, it turns into bromine. So selenium-81 transmutes into bromine, and we have an electron for beta negative decay. Here we're asked to look at beta positive decay. This is when we give off a positron as our a beta particle. And for strontium, 90 is given to us as our mass for this strontium isotope. We can look at the periodic table to see that strontium has a number of 38. In order to give off that +1, we have to drop the Z number, that proton number, the atomic number, 38 by 1. And that brings us left on the periodic table to rubidium. So strontium 90 becomes rubidium 90 plus the positron. For electron capture, let's look at potassium 40. So when potassium 40 undergoes the electron capture, the electron is added on the left side of the equation, on the reactant side. And our product is 1 to the left of potassium. So it's actually the noble gas argon, and that is a argon 40. So here we're asked to consider some biological effects of radioactive decay, and there are some kind of gruesome things that you'll see here. Early researchers in the field of radioactivity were unaware of the hazards involved. For instance, Marie Curie died of a form of cancer called leukemia, which is a cancer that is sometimes caused by exposure to radioactivity. She used to carry test tubes of radium in her pockets during research and during her World War I service in mobile X-ray units. Although it was Henri Becquerel that discovered radioactivity, it was actually Marie Curie who coined the term. That's an interesting note. So the fact that radiation can have a biological effect on people was discovered in 1901. Henri Becquerel, traveling from Paris to London for a lecture, carried a sample of radium in his pocket. When he returned to Paris, he noticed a reddened area on his abdomen beneath the pocket. However, it was still not understood just how harmful the effects of radiation might be. Today we do know alpha particles, beta particles, and gamma rays all pose danger to living tissue because they can ionize or strip the electrons from atoms. These types of radiation that ionize atoms are known as ionizing radiation. When ionizing radiation makes contact with living tissue, it can result in burns, tumors, and other harmful effects. So it's important to protect bodily tissues from exposure to ionizing radiation. So you can copy this down for ionizing radiation. So when you have atoms that are losing their electrons, it could result in burns and tumors. While gamma radiation has the greater ability to penetrate living tissue, a contact source that is an alpha emitter can do more damage than either a beta or gamma radiation because of its positive charge and relatively high mass. So that alpha particle, being a helium particle, has a higher mass versus a beta particle or a gamma particle. Fortunately, alpha particles travel a relatively short distance before becoming absorbed, so their potential danger is minimal unless they are ingested or inhaled. Beta particles and gamma rays, however, have a greater penetrating range in air and thus must be shielded against. So an alpha particle will stop at your skin, a beta particle will get into your tissue. A gamma particle will go through your skin, tissue, bone, and organs. So for ionizing radiation, the three types are alpha, beta, and gamma radiation. The particle for each is either a helium nucleus, an electron, or a positron for alpha and beta. Gamma radiation is a photon. You can see the mass of the photon is 0. The relative mass of a helium nucleus is much larger than a beta particle. The charges are listed there as +1, -1, +1, and their speeds are listed. The beta particle is almost going at the speed of light, whereas the gamma particle moves at the speed of light. And you can see here the ionizing ability. Strongest is alpha, beta is weaker, gamma is the weakest. This might not seem to be as relevant to you, but it will be important when you get to your grade 12 course. Alpha and beta particles are deflected by a magnetic field. That means that they are electrically charged. Gamma particles pass through an or a magnetic field because they are uncharged. So please copy that down as well. Sources of radiation can be divided into two main categories. We have natural or background radiation, and we have artificial radiation. Our bodies are continuously exposed to many sources of radiation around us. And you can read that on your own there. It's a list of different types of radiation that we're exposed to. You probably want to reduce the amount of radiation that you're exposed to keep you healthy. This is why you shouldn't take too many x-rays, or definitely not take unnecessary x-rays. So that's why you're always asked your consent before taking an x-ray. Another way to reduce the amount of radiation is to avoid second or first-hand smoke. Research suggests that smoke particles act as a collecting agent for radioactive particles that are already in the air. In addition, radioactive nuclides in tobacco smoke itself, such as polonium-210, attach themselves to smoke particles. And when these smoke particles are inhaled, lung tissue is bathed in close-range doses of deadly radiation. So here are some sources of radiation. We have natural sources like radon gas and minerals in the ground, cosmic radiation, and food. Artificial sources like X-rays, industrial radiation, and two ways to reduce it. Try to avoid X-rays and avoid second and first-hand smoke. So there are actual radioactive devices in your home. Your smoke detector actually uses nuclear radiation technology. We talked about smoke being a good collector of radioactive particles. Well, smoke detectors, a lot of them use an isotope of americium, and they detect smoke by absorbing basically seeing how much nuclear radiation is absorbed. And once a lot of it is absorbed, then the smoke detector determines that it's being absorbed because of the smoke. So the device ends up making a noise. This slide here talks about an ionization chamber. It says ionization chamber smoke detectors contain a small amount of radioactive material encapsulated in a metal chamber. They take advantage of ions created by ionizing radiation and develop a low but steady electrical current. So this is talking about the smoke detector. Smoke particles entering the chamber disrupt the current and trigger the detector's alarm. So if the smoke particles end up ionizing the particles in the smoke detector, then you would know that there is a lot of smoke, which means that there could be a fire. As for any health threats, as long as the radiation source stays in the detector, exposures will be negligible since alpha particles cannot travel very far or penetrate even a single sheet of paper. And the gamma rays emitted by americium are relatively weak. If the source were removed, It would be very easy for a small child to swallow, but even then exposures would be very low because the source would pass through the body fairly rapidly. So it's not a good idea to separate the source from the detector apparatus. So don't break open your smoke detectors to try to get to the radioactive material inside.